Hello and welcome to this section of the Physics 3 tutor. In this section we're going to continue talking about circular motion of charged particles that are moving through a magnetic field, and we're going to work a few problems to kind of give you some practice with that. So in the last section we covered the theory behind it and also listed the relevant equations. We kind of derived some of them and showed you how to calculate the velocity the radius, what's the radius of the circular motion, what's the period, what's the frequency, and we talked about the theory here. So let's apply that to our first problem. The problem says, what uniform magnetic field needs to be applied perpendicular to the beam of electrons that move at 1.3 times 10 to the 6th meters per second in order to bend the beam to a circular radius of 0.35 meters. All right, so the trick here is really just to understand what's going on, because you'll see in a second the math is not a big deal. We have a magnetic field. We say it's uniform. That means it's constant, pointed in the same direction, and uniform in terms of its magnitude. We have a beam of electrons. We're shooting that beam perpendicular to the field. All right, that's useful to know. We know the velocity, 1.3 times 10 to the 6th, and the beam is said to go in a circular orbit, obviously because it's shot inside of a magnetic field. It's going to curve. And we know the radius. So anytime you're given the radius of circular motion of a charged particle beam, there's a good bet that you're going to need to use the equation that we derived in the last section. The radius of any particle traveling in a magnetic field in terms of its orbital motion there that we had talked about in the last section is going to be the mass of that particle times the velocity of that particle divided by the charge on that particle times the magnetic field strength. Now I said this in the last section, but I want to be absolutely clear. Everything in this formula, because of the way we derived it when we drew the pictures and showed how the beam was coming in, everything in here is really an absolute value. In other words, just because it's an electron doesn't mean we put a negative sign here. If we put a negative Q, we're going to get a negative radius. That doesn't make sense. So you're only dealing with the absolute value of the charge because you only care about the radius. You don't even care which way the thing is orbiting. Charged particles that are positive are going to orbit a different direction than the guys that are negative, but the magnitude of this charge is the only thing that's going to tell you the size of that orbit. The radius is what we're trying to talk about. Magnetic field strength is an absolute value as well, so we don't really care about which way it's pointed, because again, the direction that the field is pointed is going to change the direction that the particles are orbiting. We don't care about that. We only care about the radius, so we're not talking about the direction of motion. Mass makes sense, that's just the mass. Velocity, it's important in all of these calculations when you use these little formulas for circular motion in a magnetic field. The velocity that they're talking about is really always the velocity component of your particle that's perpendicular to your field. So if you had a field coming out of the board, for instance, then the velocity you'd put in here would be the velocity of the beam that's coming in perpendicular to this field. If I shot a beam up, and then it would orbit something like this around the magnetic field lines coming out of the board. So in this problem it's pretty easy, because it says uniform magnetic field needs to be applied perpendicular to a beam of electrons. All right, so we know we have a beam of electrons, we know we have a field perpendicular to it, so the velocity that we have here, 1.3 times 10 to the 6th, is the velocity that we put in here. If you're shooting a beam obliquely in at some angle to the field, then you need to figure out what component of the velocity is perpendicular to the field, because that's the component that we cared about. And we talked about that in the last section when we drew all the pictures. All right, so let's see if we can figure this out. Okay, we said we know that the circular radius of this beam is going to be 0.35 meters, so we put 0.35 meters for the radius. Let's see, the mass. We know this is a beam of electrons, right? So the mass of an electron is 9.11 times 10 to the minus 31. That's in kilograms. You always want to work in kilograms. The velocity is 1.3 times 10 to the 6th, 1.3 times 10 to the 6th. And we can use this because we know the beam is perpendicular to our magnetic field. So again, if the beam were coming out of the board, or I'm sorry, if the magnetic field were coming out of the board, then our beam would be shot perpendicular to it, coming up from the bottom or something like that. That's what the problem is telling us, so that's the velocity we put in there. All right, on the bottom, what is the charge of this particle? The charge on an electron is negative 1.6 times 10 to the minus 19, but like I said a minute ago, we don't care about negative or positive charges. This is all dealing with absolute value, so you just put the absolute value of the charge there. And finally, the magnetic field is really what we don't know. So we just put that in there. And again, we're not going to know the direction of this field. We'll only care about the magnitude of it. So we really have everything here that we need. So what we'll do is we'll 0.35. On the top, if you multiply these two numbers together, you'll get 1.18 times 10 to the minus 24 on the top. On the bottom, you'll just have 1.6 times 10 to the minus 19 times the magnetic field. And now let's multiply this whole denominator, these two guys, let's multiply to get it over here. And when we multiply this times this, what we'll get is 5.6 times 10 to the minus 20, b, because we're carrying the b over there, multiplying as well, 1.18 times 10 to the minus 24. And then finally, to solve for b, we just take this whole term, 5.6 times 10 to the minus 20, and divide it to get it by itself. So the magnetic field strength is going to be 2.1 times 10 to the minus 5. Now, since we've been dealing in meters, and we've been dealing in kilograms, and we're dealing with meters per second and coulombs, those are all the base units. So the unit of magnetic field that we get is going to be in Teslas, because that's the base unit of magnetic field. So this is the answer. You can circle it, but you know, a lot of times people don't like to see all of this scientific notation. So if you think about it, 2.1 times 10 to the minus 5. If I scoot my decimal place one more over here, it would be 21 times 10 to the minus 6. And of course, that would be 21 microteslas, like that, 21 microteslas. So either way you want to write it's fine. All I'm doing is shifting the decimal place 1 here. That would make it 21. Then I have to adjust this times 10 to the minus 6 to make it equal to the same thing. So if I have 21 times 10 to the minus 6, that's 21 microteslas. So it's a good problem, but it's a basic problem. And what you'll see in a lot of these problem types here, the section of physics, is that once you understand what you're supposed to do, the math is really not hard. It's all a logic situation, making sure you understand what equations to use and how to use them. All right, the next problem says an electron is accelerated from rest by a potential difference of 350 volts. It then goes through a uniform magnetic field of magnitude 200 milliteslas with its velocity perpendicular to the magnetic field. Two parts of the question. What is the speed of the electron as it enters the magnetic field? And the second part is, what is the radius of its path in the magnetic field? So this is a very similar problem. We have a beam of electrons, we're accelerating it. We have this 350 volt stuff we'll have to talk about in a minute, but it's accelerated somehow. It goes through a uniform magnetic field. We know the field strength. We know that the velocity of the electrons are perpendicular to the magnetic field, which is a huge clue that our problem is not going to be that difficult, because when we derived all of these initial equations, we assumed that the velocity component we were talking about was perpendicular to B. And that's what we have here. So let's draw a quick diagram to show what we're doing. Sometimes when they get a little bit more complicated like this, it's good to do. So what I'm going to do is draw the magnetic field coming out of the board. Little dots mean the arrows of the magnetic field are coming directly to you. So this is magnetic field B coming out of the board. And you know, it's a beam of electrons, let's say, or actually it's a single electron in this case. So we'll put, you know, electron here. I'll call it like this. That's a little shorthand way of saying electron. And what we're going to basically do is shoot it into the magnetic field. And so what's going to happen is it's going to kind of come this way. And once it gets into the region of the magnetic field, looking back to the last section and how the force, you know, the V cross B force happens, it's going to basically come up and start to curve around and enter an orbit. And then from that point on, whoops, wrong way. From that point on, it's going to orbit. So here's my guy this way. And it's going to keep going around and around and around. It's sort of trapped, in other words. This is kind of what happens when an electron comes in from the sun and hits the magnetic field of Earth. It's sailing through space, no problem. Then when it enters the region of magnetic field, then the force of the magnetic field begins to curve it and to cause it to orbit like that. So if you think about the magnetic force, if you can kind of just look down here and pretend the field existed down here, if the field is coming out of the board like this, my velocity vector of my electron is going up. So V cross B, if I get my right hand, it's going to cut into V and then hit B. You would think the force would go this way, but don't forget, the force is equal to Q times V cross B. Q is an electron. Q is negative in this case. So the cross product does point this way, but since it's a negative electron, the force actually points it this way. So that's why it curves this direction and orbits this direction. Furthermore, just as an aside, this follows that rule of thumb I told you in the last section. If the field is pointed out of the board coming toward you, then positive particles are always going to orbit clockwise, and negative particles are going to always orbit counterclockwise. So this is just following that rule of thumb. It just saves you a few brain cells in thinking about cross products. But for this problem, it doesn't matter too much anyway, because it's just going to take an orbit like that. Now, the only thing that I think would trip students up too much in this problem is the first part says an electron's accelerated from rest through a potential difference of 350 volts, and then it enters a uniform magnetic field. What does it mean to accelerate something through a potential difference? That's really what confuses a lot of people at first. Well, you know, when you think about potential difference or voltage, we talked about that lots in the last several sections and also in the last volume of Physics 3 Tutor. Basically, you have a situation where you set up sort of an electric field there, and that particle, you put it in there, and if it's sitting in an electric field, like if you have a voltage drop across two plates or something, there's going to be an electric field between those two regions. If you drop an electron in, it's going to be accelerated because the field's going to push it. So when you read something like an electron is accelerated through a potential difference, that means that there's like two terminals of a battery and with a potential difference of 350 volts. Between those two terminals, there must be an electric field. That's the only way there could be a potential difference between them. And so if you drop a charged particle in there, of course it's going to zoom. So the question is, the part A is, what is the speed of this electron after it does this acceleration? This is the trick here. When you see an electron accelerate through a voltage V, then it has said to have gained so many electron volts of energy. Now that's a really important thing. A lot of you may have heard of that, electron volts. You've ever heard of that term before. An electron volt is basically a unit of energy, just like joule. In fact, there is a straight conversion factor between electron volts and joules. We usually talk about joules when we're talking about classical physics, like pushing rocks and dropping boulders and big things like that. Because it makes sense, because we can talk about work and energy and things like that. But when we're talking about individual electrons, usually when we accelerate them in the particle accelerator, we do it with electric fields. So it's much easier to measure how many volts I've accelerated this electron by, as I speed it up in some kind of acceleration chamber or something. So if I take one electron and I accelerate it through 1 volt of potential difference, that electron has gained 1 electron volt of energy. That's the unit of electron volts. And literally, it is exactly the way it reads. An electron volt is when you take 1 electron, you accelerate it through 1 volt. That is the unit of energy it is. Now, knowing that, that's sort of like conceptually, what you would know. But, so if 1 electron volt is when you take 1 electron and you accelerate it through 1 volt of potential difference, then it would stand to reason, and I'll just tell you like this, that you'll gain 350 electron volts if you take 1 electron, which is what we have in this problem, and you accelerate it through 350 volts. So which one of these do you think is going to be more energy? Well, if you take 1 electron and you accelerate it through 350 volts, it's going to be going a whole lot faster than the guy above. That's why this one has 350 electron volts of energy and this one only has 1. So in this case, this electron has actually picked up 350 electron volts. And so you just need to look in a conversion table at this point. 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. That's the conversion factor. I told you there was a straight conversion factor between electron volts and joules, and that's what it is. So to find this velocity, it's quite simple now. We know that this particle, since it accelerates through 350 volts, it has 350 electron volts of energy. And now we know the conversion factor. 1 electron volt is 1.6 times 10 to the minus 19 joules. So electron volts cancel with electron volts, and if you take 350 times this, of course, divided by 1, what you're going to get is 5.6 times 10 to the minus 17 joules of energy. So this particle, once we accelerate it through 350 volts, is going to have this much energy. This electron is going to have this much energy. No more and no less. So now it becomes a very easy problem because we know how many joules of energy this thing has, and we know that the kinetic energy of anything, or at least in classical physics, is 1/2 mv squared. And now we know what the energy is of this electron. 5.6 times 10 to the minus 17 is equal to 1/2 times the mass. We're talking about an electron, so we have 9.11 times 10 to the minus 31 kilograms. You should probably memorize that after a while, times v squared, which is really what we're trying to find. The problem says what speed is it going. So when you do all this stuff, when you divide a half over here, and when you divide by this, then what you will get is v squared is equal to 1.23 times 10 to the 14. Big number, 10 to the 14, but that's v squared. So to find the velocity, we take the square root of both sides. The velocity of this electron is 1.1 times 10 to the 7 meters per second. And that's the answer, because the first part of the problem said, what is the speed of this electron as it enters the chamber, or as it enters the magnetic field after the acceleration? The key of it is really just to understand electron volts, which is what I taught you here, and to know that since this one electron and it went through 350 volts, it has this much energy. This much energy, we just convert it to joules. After that, we stick it in the kinetic energy equation to calculate its velocity. So we know it's going 1.1 times 10 to the 7 meters per second. So that is the speed of this thing right at this moment as it enters the magnetic field region after it's done accelerating through this. You know, because really there's a, I didn't draw it here, but there's some kind of like acceleration between here and here, 350 volts. Like there's some kind of circuit or some kind of electric field really that's pushing it this direction. So after it gains that energy, the second part of the problem says, what is the radius of its path in the magnetic field B? What is the radius? So in other words, once it begins to orbit here, what is the radius of this orbit? And that's an equation that we derived in the last section. It's a pretty simple equation once you know how to use it. So the radius of its path is mv divided by the charge times the magnetic field. So we want to find the radius. So the mass of the electron that we're talking about is 9.11 times 10 to the minus 31. The velocity is the velocity that we calculated is coming straight in. Now notice I keep telling you over and over, this velocity that we use in this equation is always the velocity of the component of the velocity perpendicular to the field, v perpendicular. So because the beam is coming in perpendicular to the field, we don't have to do any more thinking. We just use this velocity that we calculated. The velocity we calculated is 1.1 times 10 to the 7, and that's in meters per second, so that's good. On the bottom, it's Q. Of course, this is an electron, so it's 1.6 times 10 to the minus 19 coulombs. Of course, it's really negative for an electron, but we always use absolute values when we talk about these little equations here. And the field strength is given to us in the problem. It's 200 milliteslas. You don't want to use milliteslas. You want to use 200 times 10 to the minus 3 teslas. So you have to do a little conversion there to get that. All right, so on the top, multiply these two numbers. You're going to get 1 times 10 to the negative 23. And on the bottom, you're going to get 3.2 times 10 to the negative 20. And then finally, the radius, when you do this division, is going to be 0.00031. And because of all of our base units, this is in meters. This is fine. You can totally leave it like this, but this is kind of an ugly amount of decimals. So we can shift it 1, 2, 3 decimal places, which would put it right before here. So it would be 0.31 times 10 to the minus 3, which would be 0.31 millimeters. So just doing a little conversion there. So if we want to shift it just to have less decimal points, we just shift it 3 places as 0.31, but then we have to change the unit to millimeters to make it equal to the same thing. So, once you know the velocity of this particle coming into the field, which we calculated in the first part, we just use the radius equation that we have right there to calculate the answer. All right, now the next problem says an alpha particle travels in a circular path of radius 4.5 centimeters in a magnetic field of 1.2 teslas. 3 questions. First one, what is the speed of the particle? Second one, what is the period of the revolution? Third one, what is the kinetic energy in electron volts? Okay, so we have a question where we're talking about an alpha particle. All right, an alpha particle. You may not know what that is. Let me talk about that for a second. An alpha particle is just basically when you have 2 protons in the nucleus, 2 neutrons in the nucleus, and no electrons at all. So there's no electrons to it. Now think about it. If it has 2 protons in the nucleus, then it would take 2 electrons to balance and make that a neutral atom, right? But it doesn't have any electrons. So an alpha particle has a charge of basically +2 because you have 2 protons in the nucleus. The 2 neutrons make it heavier, but they don't contribute to the charge. So let me write that down really quickly. An alpha particle, all right, means you have 2 protons, 2 neutrons. You don't have any electrons at all. So it's a +2 charge because of the 2 protons in there, okay? So the first question is, what is the speed of this particle? What is the speed of the particle? Let's write down what we know from the problem. All right, what we know. We're given that the circular path is 4.5 centimeters, so radius is 4.5 centimeters. The magnetic field is 1.2 Teslas. And let's just go from there. We'll kind of derive everything else that we need as we go. So the first question is, what is the speed of the particle? I don't really know where I'm going to go with this yet, but I know that I'm going to end up using this equation. mv over qb. Because I know the radius, I know the magnetic field, I know the charge, and I know the mass because I'm given what an alpha particle is. So I have everything I need to solve for this velocity. So that's the reason we're going to go that direction. So the radius, 4.5 centimeters. You never want to work with centimeters, so basically convert that to 4.5 times 10 to the minus 2 to convert that to meters. Now in the numerator on the top, the mass of this alpha particle, right? Protons and neutrons have very similar masses. If you look in a book, you'll see they're almost exactly the same. So for the purpose of this class, you can basically assume the proton and the neutron mass are equal, even though when you get into quantum physics, they're not quite equal. But for this class, they're so darn close. I mean, they're just many, many decimal points very similar. So basically, you can say that the mass of this guy is going to be 4 times the mass of a proton. And if you look the mass of a proton up, you'll see that it's 1.67 times 10 to the minus 27 kilograms. You can usually find this in the front of any physics textbook. This is the mass of a proton. We're just multiplying by 4 because we have 4 items in the nucleus, and we're basically saying they're all equal mass. The velocity of everything is over here still, and then on the bottom, the charge. What is the charge of an alpha particle? Well, it has 2 protons, 2 neutrons, so it has a +2 charge. So it's going to be 2 times 1.6 times 10 to the minus 19. Because when you think about it, the charge of proton and electron are equal and opposite. We know that the charge in the proton is 1.6 times 10 to the minus 19. So since we have 2 of them in the nucleus, we have 2 times that value. So that's the charge there. And then the magnetic field strength is just 1.2 because it's 1.2 Teslas. Really, this is the hardest part of the problem, is understanding what an alpha particle is and how to plug it in and how to do this part. Because the rest of this stuff is pretty simple. So what you're going to have is 4.5 times 10 to the minus 2 on the left. On the numerator, when you multiply these two numbers, you're going to get 6.68 times 10 to the minus 27, all times v on the top. And on the bottom, you multiply all 3 of these numbers together. You get 3.84 times 10 to the minus 19. All right? Now we'll multiply both sides by this denominator. So when we do that multiplication, we'll get 1.73 times 10 to the minus 20. And on the right-hand side, we're just going to leave this alone. 6.68 times 10 to the minus 27 times the velocity. And so finally, the velocity, when we divide both sides by this, the velocity is going to be 2.59 times 10 to the 6 meters per second. Meters per second. All right, so we now know the velocity of the particles. And this all came about because we're given what the radius of the orbit is, and we know all the other information. We just had to be smart about what we put in for the mass and the charge of this alpha particle to get the proper velocity. Now, the second problem says, what is the period of revolution? What is the period of revolution? Which means, how long does it take this alpha particle to make one complete orbit? That's what a period, really, of anything is. How long does it take to go all the way around? We derived an equation that dealt with the period. In the last section, the period of revolution, T, is usually how you call the period, 2 pi times the mass of the particle over QB, 2 pi m over b. So what we know is we have 2 pi on the top, and again, the mass is the mass of the alpha particle, 2 protons, 2 neutrons. So what we have is 4 times 1.67 times 10 to the minus 27. This 4 comes from the fact that there's 2 protons and 2 neutrons in the nucleus. That comprises the mass of this atom, or this ion, really. On the bottom, we have the charge Q. So we're using the same value of the charge. It's a plus 2 charge, so it's 2 times 1.6 times 10 to the minus 19. The magnetic field we know, which is 1.2. Okay. So when you do this, when you multiply 2 times pi times 4 times this big guy on the top, you will get 4.19 times 10 to the minus 26. And on the bottom, 2 times this, you will get 3.84 times 10 to the minus 19. And then when you divide these two numbers, take those two numbers and divide them in your calculator, you get 1.09 times 10 to the minus 7. The unit is going to be seconds because we're using base units of everything. We've got coulombs and kilograms and teslas, so we're going to have seconds, which is our base unit. So you could stop here and say this is the answer, but a lot of times you don't like to look at all this scientific notation. So if we wanted to convert this, this is very close to 10 to the minus 6. We'll move it this way, move the decimal point this way, and then it would only be times 10 to the minus 6. So it would be 0.109 times 10 to the minus 6, 0.109 microseconds. So either way you want to write this answer. You can leave it like this and leave it in seconds. If you don't like looking at all this scientific notation, just shift it one decimal. That'll make it 10 to the minus 6, so you can write it as microseconds. So that's the answer in terms of the period. The third part of the problem says, what is the kinetic energy of this ion, this alpha particle, in electron volts? So again, we talked about this. We know the conversion factor. 1 electron volt is 1.6 times 10 to the minus 19 joules. And we know the velocity of this particle. We know its velocity, 2.59 times 10 to the 6th. So the first thing we need to do is figure out how many joules that is. Kinetic energy is 1/2 mv squared, 1/2. What is the mass of this alpha particle? The mass is 4 times the mass of the individual proton. 1.67 times 10 to the minus 27. This is just the mass. And then I don't have enough room to write it here, so I will write it down here. The velocity of this guy is 2.59 times 10 to the 6, and it's squared because it's 1/2 mv squared. The reason we're doing all this stuff is so we can figure out what the kinetic energy of this guy is. So if you square this guy, then multiply by this, then multiply by 4, then multiply by 1/2, then you're going to get 2.24 times 10 to the minus 14 joules. That's how many joules of energy, and we know how to convert to electron volts. So we'll just go and say 2.24 times 10 to the minus 14 joules, and we'll convert it to electron volts by saying 1 electron volt is 1.6 times 10 to the minus 19 joules. And when we do that, we write it this way, joules will cancel with joules. So if you take this number, multiply by 1, divide by this number, what you will get is 1.4 times 10 to the 5 electron volts. You can totally leave it like that, no problem. But since this is so close to 10 to the 6th, if I just move this decimal one place this way, it'll be times 10 to the 6th. So it'll be 0.14 mega electron volt. So these are both the same number. 1.4 times 10 to the 5. If I were to shift this decimal one place this way, then I would have to shift this one place the other way to make it the same number. And then 10 to the 6 is mega. So 10 to the 6 mega electron volts. So 0.14 mega electron volts. So a lot of times when you read about nuclear power plants, or you read about plasma, or you read about particles and an accelerator like the Large Hadron Collider that's been built, any of the particle accelerators, if you read any of that stuff and they're smashing the atoms together and you hear about the energies involved, they're always talking about electron volts. It's millions of electron volts, or it's giga electron volts, or something even larger in some of the modern, bigger nuclear accelerators. So that's a very useful term to understand. Don't forget, an electron volt just means you take one electron accelerated through 1 volt. So if you have one electron accelerated through 1,000,000 volts, that one single electron has acquired 1 mega electron volt, 1,000,000 electron volts. Right? So that's kind of how that conversion factor works. And it's a straight conversion from joules, which you can look up in any physics textbook. All right, this covers our problem set that deals with charges that circulate in a magnetic field. We already learned about the fact that when we shoot a charged beam or any particle beam into a magnetic field, the force that the field exerts on that guy is going to tend to curve its motion. Once that process begins, it's going to close in on itself and keep on going basically forever, unless there's any kind of losses in the system. And so these problems have attempted to solidify that in you. And I encourage you to watch these again, work these yourself, make sure you understand the logic behind them, because as you can see, none of these calculations are that hard. None of them involve any calculus. None of them are really like super advanced as far as math goes. But just like most problems in physics, the math isn't what gets you, it's the logic of what am I doing and what does this mean, and understanding the definitions in the equation. So make sure you understand this and go on to the next subsequent sections, and we'll continue learning about applications of the magnetic field and how they interact in nature.